Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the silent paths of interstellar visitors, those ancient, lonely fragments that drift through our solar system, carrying stories from stellar nurseries we will never see. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. On a winter evening in early 2024, automated telescopes scanning the southern sky register a faint smudge of light moving against the fixed stars. The object bears a temporary designation, a string of numbers and letters that will later resolve into a name, 3Y Atlas. The I stands for Interstellar. The 3 marks its place in a very short list. It is the third confirmed visitor from beyond the solar system, the third fragment of another world's history to pass through the space between Earth and Mars, close enough to study, too fast to hold. The astronomers who confirm its trajectory work backward through orbital mechanics, tracing the path of this object through gravitational fields and velocity vectors. They find what they expected to find, what they have found twice before, what they will find in every interstellar visitor that follows. The orbit is hyperbolic. The eccentricity exceeds 1. The object arrived from interstellar space, and it will return to interstellar space, and there is no force in this solar system strong enough to capture it, to bend its path into a closed ellipse, to make it stay. Only took 4.5 billion years for humanity to notice these visitors were always here. The discovery happens quietly, without fanfare, because the universe does not announce its patterns with drama. A hyperbolic orbit is not an event. It is a description of loneliness rendered in mathematics. It means the object carries more kinetic energy than the sun's gravity can absorb. It means departure is inevitable, encoded in velocity, written into the physics of motion before the object even enters the planetary region where human instruments can detect it. By the time the light from this visitor reaches Earth's telescopes, its future is already determined. It will swing past the sun, accelerate slightly in the gravitational well, and continue outward toward the constellation from which it will never return. The pattern is absolute. Every interstellar object shares this fate. They arrive, they pass, they leave. There are no exceptions in the confirmed catalogue. 1I ʻOumuamua, 2I Borisov, 3I Atlas. Each one carries the same mathematical signature of exile. Scientists calculate the orbital elements and find eccentricities of 1.2336 values that place these objects firmly outside the gravitational architecture of bound solar system members. Comets from the Oort cloud, even those on highly elongated orbits, have eccentricities less than 1. They return. These visitors do not. The irony rests in the naming convention. Visitor implies a temporary presence, a brief encounter followed by continuation elsewhere. But for interstellar objects, the visit is not a deviation from their path. It is their path. They are not pausing, they are passing through. And the solar system is simply one more region of space they cross in a journey that began millions of years ago and will continue for millions more, or until they encounter another star, or until the slow drag of interstellar medium erodes them into dust too fine to hold identity. What remains uncertain is how many pass unnoticed. The confirmed visitors are bright enough, close enough, and moving at angles favorable for detection. But the surveys that find them cover only a fraction of the sky, and only objects that reflect sufficient sunlight register in the data. Statistical models suggest dozens of interstellar objects pass through the inner solar system each year, most of them dark, small, or oriented in ways that make them invisible to current instruments. Humanity sees 3 and infers a population, and knows the inference is conservative. The telescopes continue their work. The automated systems log positions, calculate velocities, flag anomalies. Somewhere in the outer solar system, beyond Neptune's orbit, another interstellar visitor is likely crossing the threshold at this moment, inbound or outbound, carrying the same hyperbolic signature, the same irreversible departure written into its motion. It will not announce itself. It will simply pass, as all the others have passed, as all the others will continue to pass, a procession of exiles moving through a darkness that does not distinguish between origin and destination. Only took 3 confirmed detections to recognize a universal pattern. The scientists published their findings in measured language, noting orbital parameters and velocity components, confirming interstellar origin through multiple independent observations. The Object 3I Atlas continues its trajectory, fading as it moves farther from the Sun, dimming below the threshold of detection. The telescopes turn to other targets. The data enters archives, and the pattern persists, quiet and absolute, binding every visitor in a shared geometry of departure that requires no interpretation, no theory, no speculation. Just the mathematics of objects that will never return. The mathematics of exile begins with a single number eccentricity. In orbital mechanics, this value describes the shape of a path through space, the degree to which a trajectory deviates from a perfect circle. For bound orbits planets, moons, most comets, the eccentricity falls between 0 and 1. A circle has an eccentricity of 0. Earth's orbit, slightly elliptical, measures 0.0167. Halley's comet, swinging far beyond Neptune before returning, reaches 0.967. These objects remain gravitationally bound to the Sun. They return. The eccentricity stays below 1. Interstellar visitors exceed this threshold. Their eccentricities range from 1.2 to over 3 values that place them in hyperbolic orbits, open curves that approach the Sun, bend around it, and continue outward without closing. The geometry is simple. A hyperbola has 2 branches, but an object on such a path follows only one. It arrives from infinity, in the mathematical sense, and departs toward infinity. There is no return arc. The orbit does not loop back. The visitor passes once, and the encounter is final. Only took Newton to predict this, 3 centuries before humanity confirmed it. The transition between bound and unbound occurs at eccentricity equals 1. The parabolic case, where an object has exactly enough velocity to escape but none to spare. This boundary condition is theoretical, rarely observed, a knife edge in velocity space. Real objects fall on one side or the other. Solar system natives, even those on highly elongated orbits, possess eccentricities slightly less than 1 bound by margins measured in meters per second. Interstellar visitors arrive with excess velocity. Their eccentricities comfortably above unity, carrying kinetic energy that no gravitational encounter in this system can fully dissipate. The hyperbolic trajectory reveals itself in the velocity curve. As an interstellar object approaches the Sun, it accelerates, gaining speed as it falls into the gravitational well. At perihelion, the closest point, it reaches maximum velocity, then begins to climb back out, slowing as gravity pulls against its motion. But unlike a bound comet, which loses speed symmetrically and eventually falls back, the interstellar visitor retains a net outward velocity. Even at infinite distance from the Sun, in principle, it continues moving. The approach and departure velocities differ in direction but not in magnitude. The object arrives at, say, 26 kilometers per second relative to the Sun, swings through perihelion at 87 kilometers per second, and departs at 26 kilometers per second aimed at a different patch of sky. This symmetry equals speeds at infinity. Inbound and outbound is diagnostic. It confirms that the Sun's gravity merely deflects the object, bending its path without capturing it. The deflection angle depends on how close the object passes and how fast it moves. For one ʻOumuamua, passing within U.25 astronomical units of the Sun, the deflection was significant, nearly 90 degrees. For 2I Borisov, which remained farther out, the bend was gentler. But in both cases, the post-encounter trajectory pointed away from the solar system, outbound and irreversible. Only took 3 examples to see the geometry is not negotiable. What remains mysterious is the distribution of these velocities. Interstellar objects do not arrive at random speeds. Their velocities relative to the Sun cluster around values consistent with the local motion of stars in the Milky Way's disk. This suggests most visitors originate from relatively nearby systems within a few hundred light-years and share the general orbital motion of the Sun around the galactic center. Outliers exist in theory objects ejected from distant or fast-moving stars, carrying velocities far exceeding the local average. But the confirmed visitors so far move at modest speeds, 20 to 30 kilometers per second, typical of the Sun's stellar neighborhood. The hyperbolic signature also constrains origin scenarios. An object with eccentricity far above 1 did not form in this solar system, and later gain velocity through gravitational assists. The boost required would exceed what planetary encounters can provide. These visitors arrive pre-accelerated, carrying velocity imparted by their home systems during ejection events billions of years ago. The mathematics does not specify which planet kicked them out, or whether their parent star still exists, or how long they wandered interstellar space before crossing paths with the Sun. It only confirms they arrived unbound, and will leave unbound. Gravitational scattering is efficient at this. When a small body approaches a massive planet at the right angle and speed, the encounter can transfer enough energy to exceed escape velocity. Jupiter does this to comets occasionally, flinging them onto hyperbolic orbits that remove them from the solar system permanently. The process is reversible in concept. Another star's Jupiter could have done the same, and the ejected object eventually crosses into this solar system, where it becomes someone else's interstellar visitor. The geometry is symmetric. What one system loses, another detects. Only took 4.5 billion years for some of those ejected objects to arrive here. The orbital elements are calculated with precision, semi-major axis, eccentricity, inclination, argument of perihelion. For hyperbolic orbits, the semi-major axis is negative, a mathematical convention indicating the orbit is open. The inclination describes the angle relative to the solar system's plane. Interstellar visitors show no preference for this plane, arriving from random directions, confirming they formed elsewhere and bear no memory of the Sun's protoplanetary disk. They are not natives returning. They are foreigners passing through, carrying trajectories shaped by gravitational fields light years away. The pattern is universal because the physics is universal. Any object with sufficient velocity follows a hyperbolic path. Any object ejected from a planetary system with speed exceeding escape velocity becomes an interstellar traveler, and any such traveler entering another system displays the same mathematical signature. There is no alternative geometry for exile. The hyperbola is the shape of departure, written into the motion of every visitor, confirmed in every calculation, invariant across all examples. The telescopes measure positions over weeks or months, building a dataset sufficient to constrain the orbit. The uncertainties shrink with each observation. The eccentricity resolves. The perihelion distance firms up. The outbound trajectory becomes predictable. And always, the conclusion is the same. The object is leaving, it will not return. The geometry permits no other outcome. The violence begins early. In the first 10 million years of a planetary system's formation, the protoplanetary disk, still thick with gas and dust, contains countless embryonic worlds, planetesimals ranging from kilometers to hundreds of kilometers across, colliding and merging in a chaotic dance of accretion. Gravity pulls matter together, building larger bodies. But the process is not smooth. For every successful merger, dozens of near misses occur. Close encounters that scatter smaller objects into eccentric orbits or eject them entirely. The young system churns with kinetic energy, and not everything survives the consolidation. Ejection happens through gravitational scattering, the same mechanism that governs all orbital deflections but amplified by the crowded environment of planet formation. A planetesimal approaching a growing protoplanet experiences a gravitational tug, its trajectory bending as it swings past. If the geometry is favorable, if the approach angle and relative velocity align correctly, the encounter transfers enough energy to boost the smaller object beyond escape velocity. It leaves the system. The protoplanet continues its growth, barely affected by the interaction. The ejected object enters interstellar space, carrying velocity imparted by a world that may no longer exist in recognizable form. Only took a few million years to clear the neighborhood, leaving the exiles behind. Jupiter and Saturn likely ejected thousands of objects during the solar system's youth, when their orbits were still migrating and their gravitational influence was reshaping the inner system. The NICE model, describing planetary migration in the outer solar system, predicts a spike in ejections around 500 million years after formation, when the giant planets settled into their current positions. Smaller bodies caught in resonance or scattered by close approaches received velocity kicks sufficient to escape. Some of these objects remain in the Oort cloud, barely bound, orbiting at distances where the sun's gravity weakens to near irrelevance. Others exceeded escape velocity entirely and departed. The efficiency of this process is high. Simulation suggests that for every kilogram of material retained in a planetary system, several kilograms are ejected. The ratio varies depending on the mass and configuration of the planet's systems, with multiple gas giants eject more, but the outcome is consistent. Planet formation produces debris, and much of that debris becomes interstellar. The galaxy fills with orphaned fragments, planetesimals that spent a few million years in orbit around a young star before a gravitational encounter sent them wandering. What remains uncertain is the size distribution of these ejected objects. Large bodies, hundreds of kilometers across, are rare but detectable if they pass close enough. Smaller fragments, meters or tens of meters in diameter, vastly outnumber their larger cousins but remain invisible unless they come very near. The 3 confirmed interstellar visitors likely represent the upper end of a population dominated by smaller, darker objects that transit the solar system unnoticed. The true census is unknown, constrained only by detection limits and statistical inference. Ejection is not unique to rocky planetesimals. Icy bodies from the outer regions of protoplanetary disks also scatter, carrying volatile compounds, water ice, carbon dioxide, methane that formed in the cold zones beyond the snow line. These objects become interstellar comets, indistinguishable in composition from their bound counterparts except for the velocity that carries them away. 2I Borisov, the second confirmed visitor, displayed a cometary coma rich in carbon monoxide and cyanogen, proving that icy volatiles survive ejection and interstellar travel. The chemistry matches comets from this solar system's Oort cloud, suggesting similar formation processes in different stellar nurseries. Only took billions of years for some of those icy fragments to cross paths with Earth's telescopes. The timing of ejection events matters. Objects expelled early, while the protoplanetary disk still contains gas, experience drag that alters their trajectories. Those ejected later, after the gas dissipates, travel ballistically, their paths determined solely by the velocity imparted during the gravitational encounter. The distinction affects their final interstellar speeds and directions, but not their ultimate fate. All become wanderers, unbound from the systems that formed them, moving through the galaxy's disk on trajectories that intersect other stars only by chance. Some ejected objects remain in the vicinity of their parent stars for extended periods, orbiting in highly elongated paths that take them far into interstellar space before returning. These objects are not yet fully unbound. Their eccentricities hover near 1, and perturbations from passing stars can either capture them permanently into interstellar trajectories or nudge them back into tighter orbits. The boundary between bound and unbound is permeable over geological timescales. An object barely bound today might become unbound in 1 million years, or vice versa, depending on the gravitational environment it encounters. The debris field from planet formation does not dissipate quickly. Even after the major planets stabilize, smaller bodies continue to scatter for hundreds of millions of years, a long tail of ejections driven by residual orbital chaos. Asteroid belt interactions, Kuiper belt scattering, and late-stage giant impacts all contribute to the ongoing loss of material. The solar system leaks mass steadily, adding to the interstellar population one fragment at a time, each ejection event unremarkable in isolation but cumulative over eons. Only took the presence of giant planets to ensure ejection would continue indefinitely. What remains unknown is whether any ejected objects ever return. If an interstellar wanderer, expelled from the solar system millions of years ago, encounters another star and gains velocity in the right direction, it could theoretically loop back, arriving home as an interstellar visitor indistinguishable from foreign objects. The probability is low, space is vast, and stars rarely pass close enough to redirect objects with precision, but not zero. The confirmed visitors could include, in principle, solar system natives returning after eons abroad. There is no way to confirm origin without detailed chemical fingerprinting, and even that may be ambiguous. The pattern persists regardless. Ejection events occur in every planetary system, governed by the same gravitational mechanics, producing the same result: fragments accelerated beyond escape velocity, sent into the galactic disk to wander until they encounter another star or fade into dust. The violence is not dramatic. It is simply efficient. A close pass, a velocity change, a trajectory that no longer closes. The object departs, and the system it leaves behind continues forming, indifferent to the loss. In October 2017, a telescope in Hawaii registered an object moving fast through the inner solar system, already past perihelion and outbound. The Pan-STARRS survey, designed to detect near-Earth asteroids and comets, flagged the trajectory as anomalous. follow-up observations confirmed what the initial data suggested. The object's velocity exceeded escape velocity. Its orbit was hyperbolic. It had come from interstellar space, swung past the Sun at a distance closer than Mercury's orbit, and was now departing toward the constellation Pegasus. The discovery was unprecedented. Humanity had detected its first confirmed visitor from another stellar system. The object received the designation ʻOumuamua, a Hawaiian word meaning scout, or messenger arriving from the distant past. The name carried poetry, but the object itself resisted easy interpretation. Its brightness fluctuated dramatically over an 8-hour period, suggesting an elongated shape tumbling end over end. Estimates of its dimensions ranged from 100 to 400 meters in length, with a width perhaps 1/10 of that, a ratio more extreme than any asteroid or comet previously observed. The surface appeared reddish, consistent with organic compounds altered by cosmic ray exposure over millions of years. But no coma formed, no tail developed, no outgassing appeared in spectroscopic observations. Only took 4.5 billion years for humanity to see one, and it arrived already leaving. The lack of cometary activity puzzled researchers. Objects from the outer solar system, rich in volatile ices, typically develop visible comas when warmed by the sun. ʻOumuamua showed none of this, suggesting either a composition dominated by rock and metal or a surface crust thick enough to trap volatiles beneath. Yet, as the object receded, measurements revealed a slight acceleration. Small, but detectable, pushing it away from the sun faster than gravity alone could explain. The acceleration was not random. It aligned with the direction away from the sun, consistent with outgassing, the same force that propels comets. But no gas was visible. Theories accumulated quickly. Perhaps the outgassing involved molecules like nitrogen or hydrogen, transparent to telescopes, leaving no spectroscopic signature. Perhaps the object was a fragment of a larger body, its interior exposed and depleting volatiles from within. Perhaps the tumbling rotation and elongated shape created thermal effects that mimicked outgassing. Each explanation required assumptions about composition or structure that could not be verified. The object was already too distant, too faint, fading beyond the reach of instruments before detailed studies could resolve the mystery. What remained certain was the trajectory. ʻOumuamua entered the solar system from the direction of Vega, approaching at 26 kilometers per second relative to the Sun. It passed perihelion at 0.25 astronomical units, well inside Mercury's orbit, reaching a maximum speed of 87 kilometers per second. The gravitational encounter bent its path by roughly 66 degrees, redirecting it toward the constellation Pegasus. The outbound velocity, corrected for the small acceleration, settled near 26 kilometers per second, close to the inbound speed, as expected for a hyperbolic orbit. The object would exit the solar system in roughly 20,000 years, crossing the heliopause and returning to interstellar space. Only took a few weeks of observation to confirm it would never return. The elongated shape, if confirmed, raised questions about formation mechanisms. Tidal forces during a close stellar flyby could stretch a body, or collisions could fragment a larger object into elongated shards. Alternatively, the brightness variations might reflect an irregularly shaped surface rather than extreme elongation, though models favored the latter. The tumbling rotation suggested no recent collisions. Objects freshly fragmented tend to spin rapidly about their shortest axis, while ʻOumuamua tumbled chaotically, indicating a dynamically relaxed state consistent with millions of years of travel through empty space. The inferred density, based on brightness and estimated size, suggested a composition similar to comets or carbonaceous asteroids porous, low-density material rather than solid rock, This supported the outgassing hypothesis, even in the absence of visible emissions. But the data was sparse, the objects small and distant, and the uncertainties large. Researchers published competing models, each consistent with the limited observations, none decisively ruling out alternatives. The mystery persisted, not from lack of effort, but from lack of data. What ʻOumuamua demonstrated conclusively was that interstellar objects exist, that they pass through the solar system with a detectable frequency, and that their properties defy simple categorization. It was not quite a comet, not quite an asteroid, but something in between or beyond those categories, a visitor shaped by processes in another system, carrying characteristics that do not map neatly onto solar system analogues. The discovery forced a revision of assumptions. Interstellar space is not empty. It contains material, fragments of planetary formation scattered across the galaxy, and some of those fragments pass close enough to detect. Only took one detection to prove the population exists. The scientific community responded with proposals for future mission spacecraft that could intercept interstellar visitors, instruments that could analyze their surfaces, strategies for rapid response when the next object appeared. But ʻOumuamua was already gone, fading below detection limits within months of discovery, moving outward at speeds no current propulsion system could match. The opportunity for detailed study had passed. What remained was the data positions, brightnesses, spectra archived and analyzed, reanalyzed, interpreted and reinterpreted as new models emerged. The object continues its journey, silent and dark, moving through the outer solar system at speeds that will carry it past Neptune's orbit within a few years, past the heliopause in millennia, into the interstellar medium where it will drift for millions more years before encountering another star. It carries no message, no information beyond what its motion and reflected light revealed. It is simply a fragment, tumbling through the void, following a trajectory determined by an ejection event in a system light years away, in an epoch when Earth's continents had not yet formed, when the solar system itself was younger and less ordered than it is now. The telescopes continue scanning, searching for the next visitor, knowing now that they exist, that they arrive regularly, that the galaxy is filled with fragments like ʻOumuamua, orphaned, wandering, occasionally crossing paths with stars that did not form them. The pattern is confirmed. The first visitor established it. The hyperbolic orbit, the interstellar origin, the irreversible departure. All future visitors will share these characteristics because the physics permits no alternative. In August 2019, an amateur astronomer in Crimea detected a faint comet in the constellation Cancer. The object, initially catalogued with a provisional designation, appeared unremarkable, another icy body from the outer solar system, inbound toward the Sun. But as observatories worldwide measured its position and velocity, the orbital calculations revealed something unexpected. The eccentricity exceeded 3. The trajectory was steeply hyperbolic. This was not a solar system native. It was the second confirmed interstellar visitor, arriving just 2 years after ʻOumuamua, and unlike its predecessor, it behaved exactly like a comet. The object received the designation Borisov, named after its discoverer. Its orbit brought it no closer than 2 astronomical units from the Sun, beyond Mars, far enough that temperatures remained low and volatiles stayed frozen except in the shallow surface layers. As the comet warmed, sublimating ices formed a visible coma, a hazy cloud of gas and dust extending thousands of kilometers from the nucleus. Spectroscopic observations identified carbon monoxide, water vapor, and cyanogen in the coma, molecules common in solar system comets. The chemistry was familiar. almost disappointingly so, proving that comet formation in other stellar systems follows the same physical principles. Only took 2 interstellar visitors to confirm that ice is ice, regardless of origin. The nucleus itself remained difficult to measure, obscured by the coma, but estimates placed its diameter near 1 kilometer small by cometary standards, but large enough to survive interstellar travel without complete erosion. The rotation period, inferred from brightness variations, suggested a tumbling motion similar to ʻOumuamua, though less extreme. The surface appeared reddish, consistent with organic tholins, complex carbon compounds formed when ultraviolet radiation and cosmic rays process simple molecules over geological timescales. This coloration matched the surfaces of long-period comets from the Oort cloud, objects that spent eons in cold storage before returning to the inner solar system. The coma's composition offered clues about formation conditions in Borisov's home system. The presence of carbon monoxide in significant quantities suggested the comet formed in a cold region, beyond the carbon monoxide snowline, where temperatures dropped low enough for this volatile to condense. In the solar system, this boundary lies around 25 to 30 astronomical units from the Sun in the outer Kuiper belt. Borisov likely formed in a similar zone around its parent star, accreting ices and dust in the frigid outer reaches of a protoplanetary disk before gravitational scattering ejected it into interstellar space. The ratio of carbon monoxide to water in the coma was notably high, higher than most solar system comets, but within the range observed for some Oort cloud objects. This suggested either a colder formation environment or different chemical processing during the comet's youth. The uncertainty arises because cometary compositions vary widely even within a single system, reflecting differences in formation location, timing, and thermal history. Borisov's chemistry confirms it formed in conditions similar to, but not identical with, those that produced solar system comets. Only took billions of years for this particular fragment to cross paths with human instruments. The coma's dust production rate, measured by brightness and scattering models, indicated modest activity less vigorous than some solar system comets at comparable distances, but not anomalously low. The dust grains themselves, analyzed through polarimetry and color measurements, resembled those in solar system cometary dust silicates mixed with organics, particles ranging from submicron to millimeter scales, fluffy aggregates with low density. The similarity extended to fine details, suggesting that dust formation in protoplanetary disks is a universal process, governed by the same condensation and aggregation physics regardless of stellar environment. What remained mysterious was Borisov's dynamical history. The comet's velocity relative to the Sun, about 32 kilometers per second, placed it near the middle of the expected distribution for objects moving through the local stellar neighborhood. This velocity implied an ejection from a system within a few hundred light-years, but offered no information about which star. The trajectory, traced backward, pointed toward a region near the constellation Cassiopeia, but the uncertainties spanned dozens of square degrees too broad to identify a specific parent system. The comet could have been traveling for tens of millions of years, long enough for its birth star to have moved significantly from its position at the time of ejection. The orbital inclination, steeply tilted relative to the solar system's plane, confirmed the comet's foreign origin. Solar system objects, even those on highly eccentric orbits, tend to remain near the ecliptic plane, a remnant of the protoplanetary disk's geometry. Interstellar visitors show no such preference. Arriving from random directions, their inclinations distributed uniformly. Borisov approached from above the plane, swung through perihelion, and departed southward, its path uncorrelated with the solar system's architecture. Only took a few months of observation to catalog its properties before it faded. The comet's activity decreased as it receded from the Sun, the coma shrinking as temperatures dropped and sublimation slowed. By mid-2020, Borisov had dimmed beyond the reach of all but the largest telescopes, its coma dissipating, its nucleus too faint and distant to track. The observations ceased. The data entered archives. The comet continued outward, moving at speeds that will carry it into the interstellar medium within a few decades, where it will drift for millions more years. Its volatiles slowly depleting through sporadic outgassing, triggered by cosmic ray impacts or encounters with interstellar gas clouds. The scientific legacy of Borisov is its ordinariness. Unlike ʻOumuamua, which defied easy categorization, Borisov behaved like a textbook comet, icy, active, chemically familiar. This ordinariness is profound. It suggests that planetary formation, at least in systems similar to our own, produces similar outcomes: rocky planets near the star, icy bodies in the outer regions, and gravitational scattering that ejects a fraction of both into interstellar space. The diversity of exoplanetary systems observed around other stars implies corresponding diversity in the interstellar population. But Borisov confirms that at least some fraction of that population resembles solar system objects closely. The pattern holds: hyperbolic orbit, interstellar origin, irreversible departure. Borisov shared these characteristics with ʻOumuamua, and the next visitor will share them as well, and all subsequent visitors, because the geometry and physics permit no alternative. The chemistry may vary, the size and shape may differ, but the trajectory, that open curve, that one-way passage through the solar system, remains constant. It is the signature of exile, written into every interstellar object that crosses into detection range. The newest arrival carries the designation 3I Atlas, detected in 2024 by the Asteroid Terrestrial Impact Last Alert System, a network of telescopes designed to track near-Earth objects. Like its predecessors, the object appeared first as a faint point of light moving against the background stars, its motion too swift and too angled to match any known solar system object. Orbital calculations confirm the now familiar signature eccentricity above 1, velocity exceeding escape, trajectory originating from interstellar space. The third confirmed visitor had arrived, and with it, the statistical certainty that more remain undetected, passing through the planetary region in silence, too dark or too distant to register in current surveys. The detection of 3I Atlas adds one data point to a catalog that grows slowly, constrained not by the absence of interstellar objects, but by the difficulty of finding them. These visitors are small, typically measuring kilometers or less in diameter. They do not emit light. They only reflect sunlight, and faintly. Their surfaces darkened by eons of cosmic ray bombardment. By the time they enter the inner solar system, where reflected light becomes detectable, they are already moving fast, crossing the sky at angular velocities that challenge tracking systems designed for slower, bound objects. The window for observation is brief weeks or months before they dim below detection limits and vanish back into the outer darkness. Only took 3 detections to make the invisible population statistically undeniable. Current models, extrapolating from the confirmed detections and accounting for survey limitations, suggest that dozens of interstellar objects pass within Jupiter's orbit each year. Most go unnoticed, their trajectories never intersecting Earth's line of sight at moments when telescopes happen to be looking in the right direction. The surveys cover only a fraction of the sky at any given time, and the objects spend most of their passage through the solar system too far from the Sun to reflect sufficient light. Detection requires the alignment of multiple factors: sufficient brightness, favorable geometry, and active monitoring of the correct patch of sky. The 3 confirmed visitors likely represent the upper end of a size distribution dominated by smaller fragments. For every kilometer-scale object like ʻOumuamua or Borisov, thousands of meter-scale fragments may pass undetected. These smaller objects reflect less light, require closer approaches to become visible, and fade quickly as they recede. Some may pass within Earth's orbit, closer than the Moon, and remain invisible simply because no telescope happens to capture their brief transit. The census of interstellar visitors is incomplete by orders of magnitude, a sampling bias that will persist until survey capabilities improve. What remains uncertain is the diversity within this unseen population. The 3 confirmed visitors display different characteristics: ʻOumuamua's elongated shape and mysterious acceleration, Borisov's cometary activity and familiar chemistry. 3I Atlas still under study with limited data. This small sample suggests variety, but whether it represents the full range of interstellar object properties is unknown. There may be populations of pure ice, pure rock, porous rubble piles, solid monoliths, objects with exotic compositions formed in stellar environments very different from the Sun's. The sample size is too small to constrain the distribution. Only took billions of years for these 3 to pass close enough, bright enough, to see. The waiting list grows not through new arrivals, but through improved detection methods. As surveys become more sensitive, covering larger areas of sky with shorter cadences, the detection rate will increase. Objects that would have passed unnoticed a decade ago now trigger automated alerts, flagging anomalous trajectories for follow-up observation. The transition from rare discoveries to routine detections is already underway, visible in the decreasing time intervals between confirmations 7 years from ʻOumuamua's passage to Borisov, 5 years to 3I Atlas. The trend will continue, accelerating as next-generation telescopes come online. The statistical models incorporate assumptions about the density of interstellar objects in the galaxy, the fraction that enter the solar system, and the biases inherent in detection methods. These models predict populations, not individuals. They estimate how many objects of a given size should pass within a given distance over a given time period. The predictions are uncertain, varying by factors of 2 or 3, depending on assumptions about ejection rates and galactic stellar density, but all models agree on the core conclusion: interstellar visitors are common, and humanity has seen only a tiny fraction of those that pass. The objects themselves carry no markers of origin, no labels identifying their parent systems. Their velocities and directions provide weak constraints. Borisov came from the general direction of Cassiopeia, ʻOumuamua from near Vega, but the uncertainties are large, and stars move. Tracing a visitor back to its source requires knowing not just its current trajectory, but the gravitational perturbations it experienced over millions of years of travel. The influences of passing stars and molecular clouds, the subtle accelerations from outgassing or radiation pressure. The reconstruction is impossible with current data. Only took 3 examples to confirm the pattern, but not to explain the origins. What 3I Atlas adds to the catalog is another confirmation of the universal signature: hyperbolic orbit, interstellar velocity, one-way passage. The details of its composition and structure await further study. Observations that may or may not occur depending on brightness and available telescope time. But the trajectory is already determined, the departure inevitable. It will swing past the Sun, perhaps revealing chemical clues or surface properties, perhaps remaining enigmatic like ʻOumuamua, and then it will continue outward, fading from view, joining the vast population of undetected objects that fill the space between stars. The catalog updates 3 confirmed interstellar visitors, detection dates and orbital parameters archived, papers published and cited. The telescopes continue their surveys, automated systems scanning for motion, algorithms flagging anomalies. Somewhere beyond Neptune's orbit, another visitor may already be inbound, carrying the same hyperbolic signature, approaching the moment when reflected sunlight will make it briefly visible. Or it may have passed months ago, unnoticed, its trajectory never intersecting a telescope's field of view. The uncertainty is asymmetric. Humanity knows when it has detected a visitor, but never knows how many it has missed. The pattern persists, unaffected by human observation. Interstellar objects arrive, pass, depart. They do not slow down. They do not orbit. They do not return. The geometry is fixed, written into their motion before detection, unchangeable by any force the solar system possesses. The list grows slowly, each new entry confirming what the previous entry's established visitors are common. Departure is certain, and the space between stars is filled with fragments that humanity is only beginning to see. Far beyond Neptune's orbit, in the cold outer reaches of the solar system, a vast spherical cloud of icy bodies surrounds the sun. The Oort cloud, named for the astronomer who predicted its existence, extends from roughly 2,000 astronomical units to perhaps 100,000 astronomical units halfway to the nearest star. This region contains billions of comets, most of them barely larger than mountains, composed of water ice, frozen gases, and rocky dust. They orbit the sun so slowly that a single revolution takes millions of years. Their gravitational binding to the solar system is tenuous, measured in tiny fractions of orbital velocity, a margin so slim that passing stars can perturb them into new trajectories. These objects are the solar system's memory of ejection events that almost succeeded. Most Oort cloud comets formed in the region between Jupiter and Neptune, in the same zone where the giant planets accreted. Gravitational encounters with these planets, particularly Jupiter, scattered the comets outward, some into elliptical orbits, others onto near-escape trajectories. Those that gained almost enough velocity to leave but not quite settled into distant, barely bound orbits at the gravitational edge of the solar system. They did not escape, but they came close, their eccentricities approaching one. Their aphelia, extending into interstellar distances, only took a few million years to populate the cloud with the almost exiled. The distinction between an Oort cloud comet and an interstellar object is a matter of velocity measured in meters per second. A comet with an eccentricity of 0.9999 remains bound, its orbit closing after millions of years. An object with eccentricity 1.001 is unbound, its path open, its departure certain, the difference at perihelion. The point of closest approach to the Sun may be imperceptible, a fraction of a kilometer per second in a velocity already measured in tens of kilometers per second. Yet that small difference determines whether the object returns or leaves forever. The Oort cloud thus serves as an observatory for understanding ejection mechanics. By studying the orbits of long-period comets that fall inward toward the Sun, astronomers can infer the processes that place them in distant orbits. The distribution of orbital energies, the inclinations and eccentricities, all carry information about the scattering events that occurred billions of years ago. Some comets show signatures of single strong encounters with Jupiter, velocity kicks large enough to send them directly into Oort cloud orbits. Others display evidence of multiple weaker interactions, a gradual diffusion outward through repeated planetary flybys. What remains uncertain is the total mass of the Oort cloud. Direct detection is impossible. The individual comets are too small and too distant to reflect detectable sunlight unless they approach the inner solar system. Population estimates rely on extrapolating from the number of long-period comets observed falling inward. Assuming these represent a fraction of the total, the estimates range from a few Earth masses to 20 Earth masses, a factor of 10 uncertainty reflecting the difficulty of counting objects that cannot be seen. Only took billions of years for a tiny fraction to fall back inward where they become visible. The cloud structure is not uniform. The inner Oort cloud, sometimes called the Hills cloud, lies between 2,000 and 20,000 astronomical units and contains comets on moderately inclined orbits. The outer Oort cloud extends beyond, forming a roughly spherical shell with no preferred plane, its members orbiting at inclinations distributed randomly. This spherical distribution is itself a product of perturbations. Passing stars and galactic tidal forces gradually randomize the inclinations of objects that began in or near the ecliptic plane. Over hundreds of millions of years, the memory of the protoplanetary disk's geometry fades, replaced by the isotropic distribution observed today. Passing stars perturb the Oort cloud continuously, though the effects are subtle over human timescales. A star passing within a light year, an event occurring roughly once every million years, can alter the orbits of outer Oort cloud comets, sending some inward toward the Sun and others outward into unbound trajectories. The star's gravity acts as a weak impulse, changing velocities by small amounts, but those small changes accumulate. A comet nudged slightly inward may fall toward the Sun over the next million years, becoming a visible long-period comet. A comet nudged outward may cross the threshold into hyperbolic velocity, joining the interstellar population. The process works in reverse as well. Interstellar objects passing through the outer solar system can, in principle, lose velocity through gravitational interactions and become captured into Oort cloud orbits. The probability is low. Most visitors pass through without encountering anything massive enough to alter their trajectories significantly, but over billions of years, some fraction of interstellar visitors may settle into distant bound orbits, indistinguishable from native Oort cloud comets, except through detailed chemical analysis. The cloud may contain foreign objects. Immigrants from other systems, mixed with the natives, only took the galaxy's slow churn to make capture occasionally possible. What the Oort cloud demonstrates is the provisional nature of gravitational binding at extreme distances. The comets orbit the Sun, but weakly. Their orbital energy is so small that external perturbations matter. The Sun's gravity at 50,000 astronomical units is barely stronger than the cumulative gravitational influence of nearby stars and the galaxy's tidal field. The comets exist in a contested region, bound to the Sun but vulnerable to outside forces. Their long-term stability uncertain over timescales of tens or hundreds of millions of years. Some Oort cloud comets will eventually be lost, nudged into unbound trajectories by stellar encounters or galactic tides. Others will fall inward, their orbits evolving through perturbations until they approach the planetary region, where they may collide with a planet, fragment near the Sun, or receive another velocity kick that ejects them. The cloud is not static. It gains and loses members continuously, a slow exchange with the interstellar medium that operates over geological time. The solar system's contribution to the interstellar population continues today, at a reduced rate compared to the violent early epochs, but still ongoing. Every long-period comet that receives a close encounter with Jupiter has some probability of being ejected. Every Kuiper Belt object that scatters inward and interacts with Neptune can gain enough velocity to escape. The process is slow, measured in objects per million years rather than per year. But it does not stop. The solar system leaks material steadily, adding to the galaxy's inventory of wandering fragments. Only took the presence of the Oort cloud to illustrate how close bound and unbound really are. The comets in their distant orbits carry no knowledge of this future. They move slowly, silently, through the outer darkness, their surfaces cold enough to preserve volatiles from the solar system's formation. Some will remain in the cloud for billions more years, orbiting until the sun exhausts its hydrogen and begins expanding into a red giant. Others will depart sooner, perturbed onto trajectories that carry them inward or outward, into fire or exile. The distinction is written in velocity, in small differences that accumulate over time, in the gravitational tug of a passing star that will not return. Stars do not remain fixed in space. They orbit the galactic center, each following its own path through the Milky Way's gravitational field, moving at velocities measured in tens or hundreds of kilometers per second. The Sun travels at roughly 220 kilometers per second relative to the galactic center, completing one orbit every 225 million years. Other stars move at different speeds, in different directions, their paths crossing and diverging as the galaxy rotates. Occasionally, two stars pass close enough that their gravitational fields overlap, and the outer regions of their planetary systems, the distant, weakly bound comets, feel the tug of both. A close stellar encounter, defined as a passage within 1 or 2 light years, occurs roughly once every million years for a typical star. The approaching star does not collide with anything. Space is too empty for that. But its gravity perturbs the orbits of objects in the outer Oort cloud, changing their velocities and trajectories through a process that operates over thousands of years as the star approaches, reaches closest approach, and recedes. The perturbations are small changes of a few meters per second, but sufficient to alter orbits that are already barely bound. Only took billions of years for the Sun to experience thousands of these encounters. The effect depends on the geometry of the encounter. A star passing through the plane of the Oort cloud, moving perpendicular to the Sun's position, exerts tidal forces that compress the cloud on one side and stretch it on the other. Comets in the compressed region experience inward perturbations, their perihelia dropping toward the inner solar system. Comets in the stretched region gain energy, some crossing into unbound trajectories. The magnitude of the effect scales with the passing star's mass, and the distance of closest approach, a massive star passing at half a light year, perturbs more comets than a low-mass star passing at 2 light years. The perturbations work both ways. Just as the passing star sends some of the Sun's Oort cloud comets into interstellar space, the Sun's gravity perturbs the passing star's own Oort cloud, if it has one. The exchange is symmetric. Each star loses some comets and potentially gains others. Though capture requires very specific geometries and velocities, most objects simply experience a velocity change that alters their orbit around their parent star, or ejects them entirely, sending them into the galaxy as interstellar wanderers. What remains uncertain is the cumulative effect over billions of years. The Sun has likely experienced several thousand close stellar encounters since its formation, each one perturbing the Oort cloud slightly, eroding its outer edge, sending a fraction of its members into interstellar space. The current Oort cloud is what remains after this long attrition comets that survived multiple perturbations, never quite gaining enough velocity to escape. The original population, established during the solar system's youth, was larger. Stellar encounters have been reducing it steadily. Only took the galaxy's slow traffic to ensure no Oort cloud remains pristine. The closest known stellar encounter in the Sun's recent past occurred about 70,000 years ago, when a binary system known as Schultz's star passed within 0.8 light-years, traversing the outer Oort cloud, The encounter was discovered through backtracking the star's current motion, calculating its trajectory through space, and determining where it had been. At its closest approach, Schultz's star would have perturbed comets in the outer cloud, sending some inward on long looping orbits that have not yet brought them into the inner solar system. Those comets may arrive in the next few 100,000 years, falling toward the Sun, becoming visible as long-period comets whose origin traces back to a stellar encounter humanity did not witness. Future encounters are predictable only statistically. The positions and velocities of nearby stars are known well enough to project their paths forward, but the uncertainties grow with time. A star currently 10 light-years away, moving at typical galactic velocities, might pass within 1 light-year in a million years, or it might miss by 5 light-years. The margin of error is large. What is certain is that encounters will continue occurring, at a rate determined by the local stellar density and the Sun's motion through the galaxy. The perturbations will continue. The Oort cloud will continue losing members, and some of those lost members will enter other stellar systems as interstellar visitors. The conversation between stellar systems is gravitational and impersonal. No information is exchanged, no signals sent. A passing star does not know it is perturbing comets, and the comets do not know they are being perturbed. The process is mechanical, governed by equations of motion that care nothing for origin or destination. A comet nudged into an unbound trajectory becomes an interstellar object, indistinguishable in flight from comets ejected by planetary scattering or any other mechanism. The method of ejection leaves no signature on the final trajectory. Only took gravity to make stellar systems leak into one another. What this process ensures is a steady flow of material between stars, a slow mixing of the galaxy's planetary debris. Comets ejected from the Sun's Oort cloud by stellar encounters will eventually pass through other stellar systems, and comets from those systems will pass through the Sun's. The timescales are long millions of years between ejection and the next stellar encounter, but the volume of space is large, and the number of stars is large, and over billions of years the exchange becomes significant. The interstellar medium contains fragments from countless systems, a diffuse population of wanderers that will never return home. The perturbations are not limited to stellar encounters. The galaxy itself exerts tidal forces, the cumulative gravitational pull of all the stars and dark matter distributed through the Milky Way's disk and halo. These tidal forces are weaker than those from a close stellar passage, but they are continuous, acting over the entire lifetime of the solar system. The galactic tide compresses the Oort cloud along one axis and stretches it along another, gradually pumping energy into comet orbits, sending a slow trickle of objects inward or outward. The tide's effect is strongest in the outer Oort cloud, where the Sun's gravity is weakest and external forces matter most. Comets at 50,000 astronomical units feel the galactic tide as a persistent perturbation, a force that never turns off, slowly altering their orbits over millions of years. Some comets gain energy, their aphelia extending farther until they cross into unbound trajectories. Others lose energy, their orbits contracting slightly, though this is less common. The net effect, over billions of years, is a slow erosion of the cloud's outer boundary. Only took the presence of other stars to ensure no comet remains isolated forever. The process has no end point. As long as stars move through the galaxy, close encounters will occur. As long as the galaxy's tidal field exists, perturbations will continue. The Oort cloud will keep losing members, some falling inward as long-period comets, others departing into interstellar space, and other stars' Oort clouds will lose members too, some of which will pass through the solar system as interstellar visitors, hyperbolic and transient, carrying the signature of ejection that no gravitational encounter can erase. The conversation is one way. Stars speaking in fragments, messages sent but never received, a dialogue of exile conducted over geological time. The chemical composition of interstellar visitors remains largely unknown. Spectroscopy. The analysis of light reflected or emitted by an object requires sufficient brightness and favorable geometry for small, dark bodies passing quickly through the inner solar system. These conditions rarely align. ʻOumuamua yielded only broadband colors, suggesting a reddish surface consistent with organic compounds, but offering no detailed molecular inventory. Borisov's active coma provided more information: carbon monoxide, water, cyanogen, but the nucleus itself remained hidden beneath the outgassing material. 3I Atlas, still under observation at the time of analysis, may reveal additional details or may fade before spectroscopic studies can constrain its composition. The challenge is observational. Interstellar objects are faint, typically reaching apparent magnitudes of 20 to 27 at their brightest, comparable to faint galaxies or distant asteroids. Large telescopes with sensitive spectrographs can collect enough light to detect strong absorption or emission features, but only if the object passes close enough and remains visible long enough. Most interstellar visitors do neither. They pass beyond Mars's orbit, too distant for detailed study, or they approach closer but move too fast, crossing the sky in weeks and fading below detection limits before comprehensive observations can be scheduled. Only took 3 detections to reveal how little spectroscopy can capture. What remains unknown is whether interstellar objects differ chemically from solar system bodies. The limited data from Borisov suggests similarities: water ice, carbon monoxide, simple organics, but this may reflect observational bias. Comets are easier to study than inert rocky objects because their outgassing produces bright comas and allows for gas phase spectroscopy. A purely rocky interstellar visitor, like a fragment of an exoplanet's crust, would be nearly impossible to characterize without a spacecraft encounter. It would reflect sunlight, appearing as a faint moving point, but its surface minerals would require near-infrared spectroscopy at high signal-to-noise ratios difficult to achieve for a rapidly receding object. The possibility of exotic compositions exists, but remains unconfirmed. A visitor from a system very different from the Sun's, perhaps one with a massive protoplanetary disk rich in refractory metals, or one where unusual chemical pathways dominated, might carry minerals or molecular signatures unknown in solar system samples. Pure metallic objects, fragments of differentiated protoplanets disrupted by collisions, could exist in the interstellar population. Nitrogen-rich ices, proposed as a possible explanation for Oumuamua's acceleration, would appear nearly invisible in most spectroscopic observations, their features weak or absent in optical wavelengths. The uncertainty extends to surface properties. Cosmic ray bombardment, acting over millions of years of interstellar travel, alters surface chemistry. High-energy particles break chemical bonds, create radicals, drive reactions that cannot occur at the low temperatures of interstellar space otherwise. The result is a processed surface layer, chemically distinct from the interior, often darkened and reddened by the formation of complex organic polymers. This radiation-damaged crust may be only micrometers thick, but it dominates the reflected light, masking the underlying composition. Only took millions of years of cosmic ray exposure to erase the original surface chemistry. Detecting water ice on an interstellar object requires near-infrared spectroscopy, where water's absorption features appear prominently around 1.5 and 2.0 micrometers. But water ice on a surface exposed to cosmic rays becomes amorphous, loses crystallinity, and may be mixed with radiation-damaged organics that alter the spectral features. The detection requires careful modeling, comparison with laboratory samples, and sufficient signal-to-noise ratios, all difficult to achieve for faint, fast-moving targets. Most interstellar visitors will pass uncharacterized in this regard. Their water content inferred or assumed rather than measured. Organic molecules: methane, ethane. More complex hydrocarbons can be detected through their absorption bands in the near-infrared, but again, only with adequate light. The organic tholins that likely coat many interstellar surfaces have broad, smooth spectra, lacking sharp features, making them difficult to distinguish from simple mixtures of rock and ice. A surface covered in radiation-processed organics might appear featureless in spectroscopy, revealing nothing about the volatiles or minerals beneath. What spectroscopy has confirmed, in the limited cases where it succeeded, is that interstellar visitors are not radically alien. Borisov's coma contained molecules found in solar system comets. The colors of ʻOumuamua and other candidates match the range observed for asteroids and cometary nuclei. This suggests that the basic chemistry of planet formation, condensation of ices and silicates, aggregation of dust, incorporation of volatile gases operates similarly across different stellar environments. The building blocks are the same: hydrogen, carbon, oxygen, nitrogen, silicon, iron. The proportions and processing may vary, but the elemental palette remains consistent. Only took 2 billion years of stellar nucleosynthesis to ensure the palette is universal. What remains elusive is the mineralogy of rocky interstellar objects. Silicate minerals, olivine, pyroxene, feldspars dominate rocky bodies in the solar system, formed through condensation in the protoplanetary disk and subsequent thermal processing. Do other systems produce the same minerals, or do different temperature and pressure profiles during formation yield different crystal structures? The question cannot be answered without detailed spectroscopy or, ideally, sample return. Neither feasible with current technology for fast-moving interstellar visitors. The possibility of detecting biosignatures, chemical traces of life, on interstellar objects has been considered and deemed unlikely. Any biological material exposed to the interstellar environment would be sterilized by cosmic rays within thousands of years. Even if an object was ejected from a habitable world carrying microbial life in subsurface pockets, the surface would be radiation damaged. And detecting life's chemical signatures would require drilling or sample collection, far beyond what remote spectroscopy can achieve. The question persists in scientific literature not because evidence exists, but because the possibility cannot be completely excluded without comprehensive data. The chemical silence, then, is a product of distance and speed. Interstellar objects pass too quickly through the narrow region where spectroscopy is feasible. They are too faint, too small, too far. The instruments capable of detailed chemical analysis require bright, stable targets conditions that interstellar visitors rarely provide. What remains is inference, extrapolation from the few successful measurements, assumptions based on solar system analogues. The true chemical diversity of the interstellar population remains hidden, awaiting better telescopes, closer encounters, or spacecraft missions capable of intercepting these fleeting visitors before they fade back into the dark. The question of panspermia, the transfer of life between worlds, persists quietly in scientific literature, neither proven nor disproven, residing in the space between plausible mechanism and absent evidence. The idea is old, predating modern biology, rooted in the observation that life appears quickly in Earth's geological record, as if waiting for conditions to permit it rather than requiring time to originate. If life can survive ejection from one world, travel through interstellar space, and seed another, then the origin of life becomes a galactic question rather than a planetary one. Interstellar objects, drifting between stars, could serve as vessels. The mechanism is straightforward in concept. A large impact on a planet with microbial life ejects fragments into space. Some fragments, particularly from near-surface locations, are accelerated to escape velocity without being sterilized by shock heating. These fragments, now interstellar objects, carry dormant microbes embedded in rock matrices, shielded from radiation by centimeters or meters of surrounding material. The fragments drift through the galaxy for millions of years. Eventually, one enters another planetary system, encounters a world with an atmosphere, and falls as a meteorite, delivering its microbial cargo to a new environment. Only took the realization that impacts can eject material without sterilizing it entirely. The survival requirements are severe. Microbes ejected into space face hard vacuum, extreme cold, and continuous bombardment by cosmic rays and ultraviolet radiation. Laboratory studies suggest that certain extremophiles organisms adapted to harsh environments can survive these conditions if protected by sufficient shielding. Bacterial spores, metabolically dormant and encased in protective layers, have survived exposure to space conditions on the exterior of spacecraft for months. Whether they could survive millions of years of interstellar travel is unknown, but not thermodynamically impossible. Cosmic ray damage accumulates over time. High-energy particles penetrate rock, breaking chemical bonds, damaging DNA, creating reactive radicals that degrade organic molecules. The shielding depth required to protect microbes for a million-year journey is estimated at 1 to several meters, depending on the cosmic ray flux and the organism's radiation tolerance. A small interstellar object, meters across, could in principle provide sufficient shielding in its interior. Larger objects offer more protection, but are rarer and less likely to be ejected by impacts. What remains uncertain is whether any ejected fragments actually carry viable organisms. Impacts energetic enough to accelerate material to escape velocity generate extreme pressures and temperatures. Most ejecta is shock heated to thousands of degrees, vaporizing organic material. But simulations suggest that some near-surface fragments, ejected by spallation during the initial shockwave propagation, experience lower peak temperatures and could preserve organic molecules or even living cells. The fraction of ejecta meeting these conditions is small, perhaps 1 in a million fragments, but over geological time. The number of ejection events is large. Only took billions of impacts across billions of planets to ensure some viable fragments might exist. Mars is often cited as a potential source. The planet has lower gravity than Earth, making ejection easier, and its geological history includes a period when liquid water existed on the surface conditions possibly suitable for microbial life. Martian meteorites found on Earth confirm that material can be transferred between planets in the same system. Extending this to interstellar scales requires only time and larger ejection velocities. If Mars hosted life in its wetter past, some fraction of impact ejecta might carry dormant Martian microbes. Now wandering the galaxy as interstellar objects, the delivery mechanism requires the interstellar object to encounter a planet with an atmosphere. Entry heating during atmospheric passage is intense temperatures reach thousands of degrees, sufficient to sterilize surface layers. But the interior of a sufficiently large meteorite can remain cool, protected by ablation of the outer material. Meteorites recovered on Earth sometimes contain unmelted interiors, minerals that never exceeded a few hundred degrees during entry. A meter-scale interstellar object, if it survived atmospheric entry intact, could deliver shielded interior material to the surface. The probability of this chain of events ejection with viable organisms, survival during interstellar travel, encounter with a suitable planet, successful delivery is vanishingly small for any individual fragment, but the number of opportunities over billions of years, across billions of planetary systems, makes the cumulative probability non-zero. Panspermia is statistically possible, in the sense that the chain of required events does not violate known physics or biology. Whether it has actually occurred remains unknown. Only took the absence of evidence to keep the hypothesis alive in peer-reviewed literature. What confounds testing is the difficulty of distinguishing between local origin and interstellar delivery. If life on Earth originated via panspermia, arriving on an interstellar object billions of years ago, no chemical or genetic signature would necessarily remain. Terrestrial life has evolved for 4 billion years, adapting to Earth's environment, diverging into millions of species. Any trace of non-terrestrial origin would be overwritten by evolution, leaving no detectable marker. The hypothesis makes no unique predictions that differentiate it from local abiogenesis. Detecting active panspermia, the current transfer of life between systems, would require finding viable organisms in interstellar objects or their impact sites. No such detection has occurred. Meteorites, including those from Mars, have been searched for microfossils or biochemical traces of extraterrestrial life. The results are ambiguous at best, with claimed detections later attributed to terrestrial contamination or non-biological processes. Interstellar meteorites, if they arrive on Earth, are indistinguishable from solar system meteorites without detailed chemical analysis, and no confirmed interstellar meteorite has been recovered. The hypothesis persists not because evidence supports it, but because it cannot be falsified with available data. Panspermia remains a possibility, filed under mechanisms that could explain the rapid appearance of life on Earth, the apparent universality of biochemistry, the resilience of extremophiles. It is neither mainstream nor dismissed, occupying a liminal space in astrobiology where speculation meets plausible physics. Interstellar objects, drifting through the galaxy, could serve as vectors. Whether any actually do is unknown. Only took the discovery of interstellar visitors to make the hypothesis slightly less speculative. The galactic recycling implied by panspermia, organic molecules and possibly life itself transferred between systems over billions of years, would make the origin of life a distributed event, not localized to single planets. If true, then the question, where did life originate, has no single answer. It originated in multiple places, or perhaps once in one place and spread, or perhaps continuously through chemical evolution occurring in interstellar clouds and delivered to planets via comets and meteorites. The scenarios multiply, each plausible in isolation, none confirmed by observation. What remains is the quiet persistence of the idea. Papers are published periodically, proposing mechanisms, calculating survival probabilities, suggesting observational tests. The scientific community treats panspermia as a legitimate hypothesis, worth investigating but not yet supported by evidence. It waits in the background of astrobiology, a possibility that would reshape understanding of life's origins if confirmed, but which may remain forever untestable. A question posed but never answered, floating in the same interstellar space as the objects that might, or might not, carry life between the stars. Velocity is the clearest signature interstellar objects carry, When astronomers measure an object's motion through the solar system, they calculate its velocity relative to the Sun, accounting for Earth's orbital motion and the Sun's position in space. Interstellar visitors arrive with velocities that differ fundamentally from bound solar system objects, not merely faster, but moving in directions uncorrelated with the ecliptic plane, carrying momentum inherited from their parent systems and modified by millions of years of galactic travel. These velocities, typically 20 to 30 kilometers per second relative to the Sun, reveal the kinematics of the local stellar neighborhood. The local standard of rest, a reference frame defined by the average motion of stars near the Sun, provides context for interpreting these velocities. Stars in the solar neighborhood orbit the galactic center at roughly similar speeds, around 220 kilometers per second. But each star has its own peculiar velocity, small deviations from this average motion. The Sun moves at about 13 kilometers per second relative to the local standard of rest, drifting slowly toward the constellation Hercules. Interstellar objects, ejected from other stars in this neighborhood, carry the peculiar velocities of their parent systems plus any additional velocity gained during ejection. Only took careful measurement to show visitors move like local stars, not like comets. The velocity distribution of interstellar objects is predicted to follow the velocity distribution of nearby stars, broadened slightly by ejection processes. Stars in the solar neighborhood have peculiar velocities typically ranging from 10 to 40 kilometers per second, with a few outliers moving faster. An object ejected from such a star gains additional velocity during the ejection event, perhaps 1 to 10 kilometers per second, depending on the mechanism, resulting in a final interstellar velocity in the range of 15 to 50 kilometers per second. This matches the observed velocities of ʻOumuamua, Borisov, and 3 Atlas, all of which fall comfortably within this predicted range. The direction of motion carries information, though less precise than the speed. Interstellar objects arrive from random directions on the sky, their trajectories uncorrelated with the solar system's structure, but their velocities are not isotropic in the galactic frame. Most move with a component of motion consistent with the general rotation of the galactic disk. Objects arriving from directions perpendicular to this rotation, or moving against it, are rarer. Such velocities would require ejection from stars with unusual galactic orbits, populations that exist but are less common in the solar neighborhood. What remains uncertain is whether any interstellar visitors originate from distant regions of the galaxy. High-velocity objects, moving at 100 or 200 kilometers per second relative to the Sun, would indicate ejection from fast-moving stars or from regions with different kinematic properties. The galactic halo, perhaps, or even extragalactic sources in extreme cases. No such objects have been detected, but observational biases favor slower-moving visitors. A fast object spends less time in the inner solar system, reducing the probability of detection. It also requires higher sensitivity to track, as its angular velocity across the sky exceeds the limits of many survey systems. Only took 3 detections to confirm most visitors are local, moving at modest speeds. The velocity also determines the object's trajectory through the galaxy. An interstellar object moving at 26 kilometers per second relative to the Sun will travel roughly 26 light-years per million years, assuming no significant gravitational deflections. Over the age of the galaxy, roughly 13 billion years, such an object could, in principle, traverse the entire disk multiple times. But space is vast, and stars are sparse. The probability of encountering another stellar system is low. Most interstellar objects will drift through the galaxy indefinitely, perturbed occasionally by stellar encounters but never captured, never colliding, simply moving until radiation pressure or collisions with interstellar gas erode them into dust. The Sun's motion through the local standard of rest means that interstellar objects appear to approach preferentially from the direction the Sun is moving toward. This is a geometric effect, analogous to how raindrops appear to come from ahead when driving through rain. The actual distribution of interstellar objects in space is roughly isotropic, but the Sun's motion creates an apparent concentration in the direction of solar apex toward Hercules. Surveys must account for this bias when estimating the density of the interstellar population. The relative velocity between an interstellar object and the Sun determines how long the object remains detectable. Faster objects spend less time in the inner solar system, passing through the detection zone in months rather than years. Slower objects linger longer but are also rarer, as their velocities would need to be closely matched to the Sun's peculiar velocity, an unlikely coincidence. The median encounter velocity is predicted to be around 30 kilometers per second, consistent with observations, though the sample size remains too small to confirm the full distribution. Only took precise astrometry to reveal velocities unchanged by the Sun's gravity at large distances. What the velocity measurements confirm is that interstellar objects are not randomly scattered debris, but products of processes operating in specific stellar environments. Their speeds match the local stellar kinematics. Their trajectories reflect ejection from planetary systems similar to the Sun's. Their motions integrate them into the broader dynamics of the galactic disk. They are not exotic, not anomalous in their velocities, simply fragments moving as stars move, carrying the momentum of their lost homes. The inbound and outbound velocities, measured at large distances from the Sun where its gravitational influence is negligible, are nearly equal in magnitude. This symmetry confirms the hyperbolic nature of the orbits. A bound object would have zero velocity at infinity. An interstellar object retains its velocity indefinitely. The difference is measurable, diagnostic, and absolute. No interstellar visitor slows to rest at aphelion. No visitor turns around. The velocity persists, carrying the object outward, away from the Sun, into the dark. The distribution of velocities in the interstellar population remains partially hidden. The confirmed detections sample the bright, slow end of the distribution objects moving slow enough to be tracked and bright enough to be seen. Faster objects pass undetected, their brief transits missed by surveys not designed to capture high angular velocities. Dimmer objects, regardless of speed, remain invisible unless they pass very close. The true velocity distribution will emerge only as detection capabilities improve, as surveys cover more sky at higher cadences, as the sample size grows from 3 to hundreds. Only took the realization that velocity is identity-bound or unbound, determined forever. The kinematics of interstellar objects ties them to the galaxy's structure, embedding them in the broader context of stellar dynamics. They move not as isolated wanderers, but as participants in the galaxy's rotation. Their velocities shaped by the same gravitational forces that govern stars. They are debris, yes, but debris in motion, carrying information about the systems that expelled them, the regions of space they traversed, the timescales over which galactic processes operate. The velocity is a record, written in motion, readable only through careful measurement of position and time. The difficulty begins with detection. Interstellar objects are small, typically measured in hundreds of meters to a few kilometers, and dark. Most reflect only a few % of the sunlight that reaches them, their surfaces aged and reddened by cosmic ray exposure. At the distances where they become visible, typically inside Jupiter's orbit, they appear as faint points of light moving against the background stars. Their apparent magnitude ranges from 20 to 27 fainter than all but the dimmest asteroids, requiring telescopes with large apertures and sensitive detectors to register. Current surveys scan the sky systematically, imaging each patch multiple times per night to detect moving objects. Asteroids and comets leave trails in these images, their motion apparent when frames taken hours apart are compared. But interstellar objects move faster, their angular velocities often exceeding the rates that survey pipelines are optimized to detect. An object crossing the sky at 2 degrees per day, typical for an interstellar visitor at 1 astronomical unit, may blur in exposures longer than a few seconds, or may move far enough between images that automated linking algorithms fail to recognize it as a single object. Only took decades of surveying to realize the pipelines were tuned for slower targets. The brightness constraint is severe. A 1-kilometer object at 1 astronomical unit from both the Sun and Earth, with an albedo of 4%, reaches an apparent magnitude near 22. This is detectable by large survey telescopes, but only in dark sky conditions, with exposures long enough to accumulate sufficient photons. Most surveys prioritize coverage over depth, imaging large areas of sky with shorter exposures, sacrificing the ability to detect faint objects in favor of detecting brighter ones across more sky. Interstellar visitors, faint and fast, fall through the gaps. The time window for detection is brief. An interstellar object entering the inner solar system from interstellar space spends only weeks or months bright enough to detect. It fades as it approaches perihelion or brightens, depending on its trajectory, and then fades again as it recedes. Once it passes beyond roughly 2 astronomical units from the Sun, its reflected light drops below detection thresholds for all but the largest telescopes. The object continues outward, invisible, its trajectory known only from the handful of observations captured during its brief passage through the detection zone. What remains unknown is how many pass at distances too great to reflect sufficient light. An object passing beyond Mars's orbit at 1.5 or 2 astronomical units from the Sun is already dim. One passing beyond Jupiter at 5 astronomical units is effectively invisible unless it is large or unusually reflective. The surveys detect only those objects that pass close enough to the Sun to brighten above detection limits, a geometric bias that skews the observed population toward closer encounters. Only took statistical modeling to infer that dozens pass undetected for every one that is seen. The angular velocity problem compounds with distance. An object moving at 30 kilometers per second at 1 astronomical unit from Earth appears to move across the sky at roughly 0.05 degrees per hour. This is fast by asteroid standards, but still trackable with careful astrometry. The same object at 5 astronomical units moves at 1/5 the angular velocity, easier to track, but much dimmer. The trade-off between brightness and trackability creates a narrow zone where detection is feasible close enough to be bright, slow enough to track, but not so close that the object has already passed and is receding. Survey cadence matters critically. A survey that images the same patch of sky once per night can link observations of an object moving at typical angular velocities, building up a trajectory over multiple nights. But if the object moves faster than expected, or if cloud cover interrupts observations, the linkage fails. The object appears in one night's images, then disappears, never recognized as a single entity moving through the solar system. Automated pipelines flag it as noise or a transient, and it is discarded. The problem is worse for objects on highly inclined orbits. Surveys prioritize the ecliptic plane, where most solar system objects reside. An interstellar visitor approaching from high galactic latitude, far from the ecliptic, spends less time in heavily surveyed regions. Its trajectory might intersect the detection zone at angles unfavorable for repeated observations, passing through in a single night before moving into unsurveyed sky. Such objects are detected only by chance, if at all. only took 3 detections to reveal how narrow the observational window really is. What limits detection most fundamentally is sky coverage. Even the most ambitious surveys image only a fraction of the sky each night, perhaps a few thousand square degrees out of the 41,253 square degrees of the full celestial sphere. An interstellar object passing through unsurveyed regions remains invisible. If it crosses the sky during daylight, or during bright moonlight that raises background levels and reduces sensitivity, it is missed. The surveys are incomplete by design, optimized for finding near-Earth asteroids and other solar system objects, not for catching the rare, fast, faint visitors from interstellar space. The situation is improving slowly. Newer surveys with larger fields of view, faster cadences, and deeper exposures are beginning to close the gaps. Telescopes like the Zwicky Transient Facility and the upcoming Vera-C, Rubin Observatory will image larger areas of sky more frequently, with sufficient depth to detect fainter objects. The Rubin Observatory, in particular, is expected to increase interstellar object detection rates by factors of 10 or more, turning rare discoveries into routine events. But even these improvements will not eliminate the bottleneck entirely. The faintest, fastest, or most distant objects will still pass unnoticed. The detection bottleneck also affects follow-up observations. Once an interstellar object is detected, confirming its trajectory requires multiple observations over days or weeks. Large telescopes with spectroscopic capabilities must be scheduled quickly, before the object fades. But telescope time is competitive, allocated months in advance, and rapid response programs have limited access. By the time spectroscopic observations can be arranged, the object may already be too faint or too far to study in detail. The discovery and the opportunity to characterize are separated by logistical delays that cannot always be overcome. Only took ʻOumuamua's passage to reveal the need for rapid response infrastructure. What this bottleneck ensures is that the observed population of interstellar visitors is a small, biased sample. The detections favor objects that are bright, slow, and favorably positioned. The full population dominated by smaller, faster, or more distant objects remains hidden, its properties inferred statistically rather than measured directly. The 3 confirmed visitors are outliers in detectability, not representatives of the norm. For every ʻOumuamua or Borisov, dozens or hundreds of similar objects pass through the inner solar system unseen. Their presence inferred, but not confirmed, ghosts in the data that surveys are not yet equipped to capture. The pattern persists: arrival, passage, departure. But humanity sees only a fraction of this procession. The brightest members of a population that extends far below current detection limits. The bottleneck is technological and geometric, not physical. The objects are there, passing through, carrying their hyperbolic trajectories and interstellar velocities. The limitation is not their absence, but humanity's inability to see them. The dark remains dark, and most visitors pass in silence. The future of interstellar object detection begins with a telescope in Chile, scheduled to achieve first light in the coming years. The Vera-C, Rubin Observatory, named for the astronomer who provided key evidence for dark matter, will conduct the legacy survey of space and time, a 10-year program to image the entire visible sky every few nights. The telescope's 8.4-meter mirror and wide-field camera will capture regions of sky spanning 9.6 square degrees per exposure, roughly 40 times the area of the full moon. Each night, the system will collect terabytes of data, detecting millions of objects and tracking their motions with unprecedented completeness. The cadence is designed to catch transient events, supernovae, variable stars, moving asteroids, But it will also revolutionize the detection of interstellar visitors by imaging the same regions repeatedly. The survey will link observations of fast-moving objects across multiple nights, building trajectories precise enough to distinguish hyperbolic orbits from bound solar system members. The depth of the images, reaching magnitude 24.5 in a single exposure, will detect objects far fainter than current surveys can reach. Statistical models predict the Rubin Observatory will detect between 10 and 100 interstellar objects per year, depending on the true density of the interstellar population. Only took decades of planning to build an instrument capable of routine detection. The increase in detection rate will transform interstellar visitors from rare discoveries into a catalog, a growing database with sufficient entries to constrain population statistics. Questions currently unanswerable. What is the size distribution? What fraction are cometary versus rocky? What is the velocity distribution will become empirically testable. The sample size will grow from 3 to hundreds within the survey's first years and to thousands by its conclusion. The patterns hidden in small number statistics will emerge clearly, revealing the structure of the interstellar population. The survey's automated pipeline will flag candidates in real time, alerting the astronomical community within hours of detection. Rapid follow-up observations with spectroscopic instruments can begin while the objects are still bright, capturing chemical information before they fade. The coordination between discovery and characterization will improve, reducing the lag that hampered studies of ʻOumuamua and limiting what could be learned. Some visitors will still pass too quickly or too faintly for detailed study, but the fraction successfully characterized will increase substantially. What remains uncertain is whether the Rubin Observatory will detect truly unusual objects, visitors from distant regions of the galaxy, or with compositions radically different from solar system bodies, or moving at velocities far exceeding the local norm. The survey's depth and coverage make it sensitive to rare outliers, but how rare these outliers are, and whether any exist at all, is unknown. The confirmed visitors so far are unremarkable in their properties, consistent with ejected planetesimals from nearby systems. The catalogue may reveal diversity, or it may confirm that most interstellar objects are similar, products of similar formation and ejection processes. Only took the realization that detection is a matter of survey capability, not object scarcity. Other surveys will contribute to the growing catalogue. The Zwicky Transient Facility, already operational, detects a few candidates per year, though confirmation requires follow-up observations and careful orbit determination. Space-based telescopes, free from atmospheric interference and capable of observing in infrared wavelengths, will add detections of objects too faint or too red for ground-based surveys. The Near-Earth Object Surveyor mission, scheduled to launch in the coming years, will scan the sky in infrared, detecting asteroids and comets, but also, incidentally, interstellar visitors that pass through its field of view. The multiplication of detection platforms ensures redundancy. An object missed by one survey may be captured by another, and cross-referencing detections will improve orbit determination. The Interstellar Object Catalog will become a collaborative effort, aggregating data from multiple telescopes and surveys, each contributing pieces of the observational puzzle. The coordination is already being planned, with protocols for reporting candidates and sharing data established through international astronomical organizations. The shift from discovery to characterization will require infrastructure beyond detection. Large telescopes with spectroscopic and imaging capabilities must be available for rapid follow-up. Spacecraft missions, capable of intercepting interstellar visitors while they are still in the inner solar system, are being proposed. The European Space Agency's Comet Interceptor mission, scheduled to launch in the late 2020s, will wait at a gravitational parking point until a suitable target, either a pristine solar system comet or an interstellar visitor, is identified. The spacecraft will then maneuver to intercept, conducting close-range studies impossible from Earth. Only took 3 detections to motivate missions capable of reaching these visitors directly. What the Rubin Observatory and similar surveys will not do is eliminate all detection biases. The faintest objects, those with diameters below a few hundred meters, will remain difficult to detect unless they pass very close. Objects on trajectories that avoid the ecliptic plane or that pass during seasons when their sky position is unfavorable will still be missed. The catalog will grow, but it will not be complete. The true population of interstellar visitors will remain partially hidden, inferred from the detected fraction through statistical models. The anticipated detection rate, tens to hundreds per year, will provide sufficient data to test theories of planetary system formation and ejection processes. By measuring the size distribution, researchers can infer how many small versus large objects are ejected. By analyzing compositions, they can constrain the diversity of protoplanetary disk chemistries. By tracking velocities and trajectories, they can map the kinematic structure of the interstellar population and identify subpopulations with unusual properties. The catalog will become a tool for understanding not just the visitors themselves, but the systems that produce them. The 10-year timeline of the Legacy Survey ensures continuity. Interstellar objects will be detected year after year, building a dataset robust enough to identify temporal trends or spatial clustering, if any exist. The survey will span enough time to detect variations in the interstellar flux, whether the rate of passages increases or decreases, whether certain types of objects are more common in certain years. The long baseline will allow for studies impossible with sporadic detections. Only took the recognition that systematic surveying, sustained over years, transforms anomalies into populations. What remains beyond the Rubin Observatory's reach are the truly distant passages objects that transit the outer solar system beyond Neptune's orbit, never approaching close enough to brighten above detection limits. These objects, if they exist in significant numbers, will remain invisible until space-based infrared surveys with greater sensitivity come online. The catalog will represent the inner solar system's visitors, but the outer system's passages will go unrecorded. A blind spot in humanity's view of the interstellar population, the legacy of the survey will extend beyond detection. Each interstellar visitor, catalogued and studied, adds to the understanding of how planetary systems evolve, how material is exchanged between stars, how the galaxy's disk is populated with fragments of worlds that no longer exist or have transformed beyond recognition. The visitors are messengers, not in any intentional sense, but in the information they carry, chemical, dynamical, structural. The Rubin Observatory and its successors will read these messages, one faint point of light at a time, translating motion and brightness into knowledge about processes operating across light years and eons. The survey begins soon. The telescope waits in Chile, its mirror polished, its camera installed, its systems tested. When it opens its eye to the southern sky, the rate of interstellar object detections will increase sharply, and the catalog will begin to fill. The rare will become common, the anomalous will become routine, and the pattern hyperbolic, transient. One way will repeat in observation after observation, confirming what 3 visitors have already shown: the galaxy is full of fragments, and some of them pass close enough to see. The scientific value of interstellar visitors lies in what they carry information about planetary systems beyond reach. Exoplanets can be detected through transit photometry or radial velocity measurements, their masses and orbits inferred from the gravitational signatures they leave on their parent stars, but their surfaces, their atmospheres, Their detailed compositions remain largely inaccessible. The light from an exoplanet is overwhelmed by its star, requiring extreme contrast ratios to observe directly. Spectroscopy of exoplanet atmospheres is possible in some cases, but only for large planets orbiting close to their stars, where atmospheric signals are strongest. The smaller, rocky worlds, those most likely to harbor conditions similar to Earth, remain beyond detailed characterization. Interstellar objects offer an alternative. They are fragments of those distant systems, ejected during formation, carrying with them the chemical and physical properties of their birth environments. A rocky interstellar visitor is, in essence, a sample of an exoplanet's crust or mantle delivered to the solar system for study. An icy visitor is a preserved comet from another system's outer regions, its volatiles unaltered except by cosmic ray processing. These objects are accessible in ways that exoplanets are not observable at close range, potentially within reach of spacecraft, subject to the full suite of analytical techniques unavailable for distant worlds. Only took the realization that debris can be more informative than intact worlds. The chemistry of interstellar visitors constrains the conditions in their parent protoplanetary disks. The presence of water ice indicates formation beyond the snowline, where temperatures dropped low enough for water to condense. Carbon monoxide, detected in Borisov's coma, suggests even colder formation regions, where this volatile could freeze. The ratio of different isotopes, carbon-12 to carbon-13, oxygen-16 to oxygen-18, carries information about nucleosynthetic processes in the parent star and the mixing of materials in the protoplanetary disk. Each chemical signature is a clue, connecting the visitor to conditions billions of years ago in a system light-years away. The size distribution of interstellar objects reflects the physics of planetesimal formation and ejection. If small objects dominate, it suggests that fragmentation collisions breaking larger bodies into smaller pieces played a significant role. If large objects are more common than expected, it implies that ejection preferentially affects bodies that grew to substantial sizes before being scattered. The distribution also constrains how much mass was ejected from typical planetary systems, allowing estimates of how much material was lost during formation versus retained in planets and smaller bodies. What remains uncertain is whether interstellar visitors can reveal information about the habitability of their parent systems. A rocky object carrying hydrated minerals, clays or serpentines that form in the presence of liquid water would suggest that water existed in the system, at least transiently. Organic molecules, if detected and characterized, could indicate prebiotic chemistry. But interpreting these signatures is difficult. Hydration and organics can form through multiple pathways, and cosmic ray processing during interstellar travel alters surface chemistry, obscuring original compositions. Only took the study of meteorites to demonstrate that fragments carry histories written in chemistry. The structural properties of interstellar visitors, density, porosity, mechanical strength provide insights into accretion processes. Planetesimals that formed through gentle collisions and gravitational aggregation tend to be porous, with significant void space between constituent particles. Those that experienced higher velocity collisions or thermal processing may be denser, more compact. Measuring these properties requires close observation or, ideally, spacecraft encounters. The tumbling rotation of ʻOumuamua and Borisov suggests neither is a solid monolith. Both likely have irregular shapes or internal heterogeneity that affects their rotational dynamics. The diversity of interstellar visitors, as the catalogue grows, will reveal whether planetary system formation is a uniform process or varies significantly between systems. If all visitors resemble solar system objects, rocky asteroids, icy comets, With familiar compositions, it suggests that the same physical and chemical processes dominate everywhere. If some visitors display exotic properties, unusual mineralogies, unexpected volatile mixtures, structures inconsistent with known formation mechanisms, it indicates greater diversity in protoplanetary disk conditions or evolution. The thermal history of interstellar objects, inferred from their mineralogy and structure, constrains how much heating they experienced during formation and ejection. Minerals that crystallized at high temperatures indicate thermal processing, either through proximity to the parent star, radiogenic heating, or shock heating during impacts. Amorphous or low-temperature minerals suggest formation in cold regions with minimal subsequent heating. These thermal signatures map the temperature gradients in protoplanetary disks, revealing how heat flowed and dissipated during planet formation. Only took the diversity of solar system objects to suggest interstellar diversity might be similar. What interstellar visitors cannot reveal is detailed information about the planets that scattered them. The ejection process is gravitational, determined by the mass and orbit of the scattering planet, but this information is not encoded in the ejected object's trajectory or composition. A fragment scattered by a Jupiter analog is indistinguishable from one scattered by a Saturn analog or by a super-Earth. The visitors carry no memory of the specific encounter that expelled them, only the velocity it imparted. The detection of parent systems, matching a visitor to its origin, remains aspirational. The trajectory can be traced backward, pointing toward a region of sky, but identifying the specific star requires knowing the visitor's age, how long it has been traveling, and accounting for stellar motions over that time. Both are difficult to constrain. The visitor's surface, processed by cosmic rays, offers limited age information. The parent star, even if identified, may have moved light years from its position at ejection. The connection is theoretically possible, but practically challenging. The long-term goal is a catalog detailed enough to perform comparative planetology across stellar systems. By analyzing dozens or hundreds of interstellar visitors, patterns will emerge, correlations between composition and inferred formation distance, relationships between size and ejection velocity, chemical signatures that cluster or vary systematically. These patterns will inform models of planetary system evolution, testing predictions about how planets form, migrate, and eject debris. The visitors become data points in a larger study of galactic planetary processes. Only took the recognition that each visitor is a probe, carrying data from systems too distant to visit. What the study of interstellar objects ultimately provides is context for the solar system. By seeing what other systems produce, astronomers can assess whether the solar system is typical or unusual. Are Jupiter and Saturn's ejection rates normal or anomalously high? Is the composition of solar system comets representative or specific to the Sun's protoplanetary disk? Do other systems undergo late heavy bombardments? Or was the solar system's impact history unique? These questions, unanswerable from studying only the solar system, become tractable when interstellar visitors provide comparison samples. The value is not immediate. Each visitor adds incremental knowledge, a single data point in a distribution that requires hundreds of points to resolve. But the accumulation is inevitable. The surveys are improving, the detection rates are increasing, the catalog is growing. Within decades, the sample size will be sufficient to draw robust conclusions, to identify trends and outliers, to constrain the processes that govern planetary system formation across the galaxy. The visitors, silent and transient, will collectively speak to the diversity and commonality of worlds humanity cannot visit directly. The pattern is singular and absolute. Every interstellar visitor detected to date shares one defining characteristic. Etched into its motion with mathematical precision, it left. The departure is not a choice, not a destination, but a consequence of velocity speed exceeding the threshold required to escape the sun's gravitational embrace. The orbit is hyperbolic, the eccentricity above 1, the trajectory open. There is no return arc, no aphelion where the object slows and reverses direction. The visitor arrives from interstellar space, swings through the solar system in a single pass, and continues outward into the dark from which it came, diminished only by the light it briefly reflected. This departure defines them more completely than their composition, their size, their origin. A visitor may be rocky or icy, pristine or processed, ancient or recently ejected. But regardless of these variables, it carries the irreversible signature of exile. The mathematics permits no ambiguity. An object with eccentricity 1.2 or 3.0 follows a path that does not close. Gravitational forces bend the trajectory, accelerating the object as it falls toward the sun, decelerating it as it climbs back out. But the net effect is deflection, not capture. The visitor departs at the same speed it arrived, aimed at a different patch of sky, moving away. Only took 3 confirmations to establish that departure is the only pattern all visitors share. The universality of this pattern arises from the physics of gravitational scattering. An object ejected from a planetary system gains velocity through close encounters with planets, most often gas giants whose mass dominates the gravitational interactions. The encounter transfers orbital energy from the planet to the smaller body, accelerating it. If the velocity gain exceeds the escape velocity from the system, the object becomes unbound. Its trajectory shifts from a closed ellipse to an open hyperbola. The transition is abrupt in mathematical terms but continuous in physical terms. There is no moment when the object becomes interstellar. It simply moves faster than the minimum required to leave. Once unbound, the object cannot be recaptured by the system that ejected it. The velocity required to reverse the hyperbolic trajectory and bring the object back into a bound orbit exceeds what gravitational interactions within the system can provide. Even a second close encounter with the same planet that ejected it would, most likely, simply deflect the trajectory further rather than slow the object enough to capture it. The phase space of capture is narrow compared to the phase space of continued departure. The visitor leaves, and leaving is final. What remains uncertain is whether any interstellar object has ever been captured into a bound orbit by another stellar system. The process is theoretically possible. An object passing through a system could, through a precise sequence of gravitational interactions, lose enough velocity to become bound. The probability is low, requiring specific geometries and multiple encounters timed correctly, but over billions of years and countless passages, some captures may occur. If they do, the captured objects become indistinguishable from native comets or asteroids. Their interstellar origin, hidden unless chemical analysis reveals discrepancies. Only took the realization that capture is rare, departure is common, and most objects leave permanently. The shared pattern extends beyond the individual visitors to the population as a whole. Interstellar objects are not a transient phenomenon, not a brief epoch in galactic history. They are a continuous presence, the ongoing product of planetary formation and scattering processes operating in every system with massive planets. As long as stars form and planets accrete, ejection will occur, populating the interstellar medium with fragments. The galaxy has been producing these visitors for billions of years, and will continue producing them until star formation ceases. The departure is also irreversible on galactic timescales. An interstellar object moving at 30 kilometers per second will travel thousands of light years over the age of the galaxy, crossing the disk multiple times if its trajectory is not confined to the plane. But the probability of returning to its origin system is vanishingly small. Stars move, their orbits around the galactic center slowly shifting position. By the time an ejected object could complete a loop and return, if such a loop were even possible, the parent star would be elsewhere, perhaps hundreds of light years away. The object and its origin diverge, never to reconnect. What binds all visitors is not origin, not composition, not age, but trajectory. The hyperbolic orbit is the signature, the shared identity, the one characteristic that can be measured unambiguously and that defines membership in the population. An object with eccentricity 0.99 is not an interstellar visitor, it is a barely bound comet. An object with eccentricity 1.01 is interstellar, regardless of how similar its other properties may be. The distinction is sharp, written into the mathematics of motion, only took the recognition that identity is encoded in velocity, and velocity determines fate. The pattern of departure also implies a pattern of arrival. Though the symmetry is incomplete, every interstellar visitor now departing the solar system once arrived, entering from the direction its current trajectory traces backward. The arrival was silent, unannounced, the object dark and cold until sunlight began reflecting from its surface. There was no transition, no boundary crossed, just the gradual brightening as the sun's light strengthened and the object entered the region where telescopes could detect it. Arrival and departure are continuous processes, the object simply passing through, its motion uninterrupted. The destinations of departing visitors are unknowable. Their trajectories point toward specific constellations. Pegasus for ʻOumuamua, a southward path for Borisov, but these directions are meaningless on interstellar scales. The object will not reach any particular star, not in any time frame relevant to human understanding. It will drift through the space between stars, the distances so vast that toward loses meaning. The trajectory extends indefinitely. The object moving until external forces, stellar encounters, collisions with interstellar gas, radiation pressure alter its path or erode it into dust. What the pattern reveals is that interstellar visitors are fundamentally different from solar system objects, not in substance but in status. They are exiles, fragments that crossed a threshold and cannot return. The solar system's comets and asteroids, even those on highly elliptical orbits, remain bound. They may take millions of years to complete an orbit, but they will return. Interstellar visitors will not. They passed through once, and the passage was final. The difference is written into their motion, irrevocable and absolute. Only took the invention of orbital mechanics to predict this, the construction of telescopes to confirm it. The universality of departure ensures that interstellar space is filled with these travelers. Every planetary system contributes, ejecting fragments during its formation and continuing to eject smaller numbers over its lifetime. The cumulative population, built over billions of years across billions of systems, is immense, far larger than the populations of bound objects in any single system. The galaxy is populated not primarily with planets, but with the debris planets left behind, the fragments scattered into the void, the exiles moving alone through the dark. The pattern will repeat in every future detection. The next interstellar visitor will arrive with hyperbolic velocity, swing past the sun, and depart. The one after that will do the same, and the one after that, indefinitely. The Rubin Observatory and its successors will catalogue hundreds, then thousands, and each will share this singular trait: it came, it passed, it left. There will be no exceptions, because the physics permits none. Objects with insufficient velocity to escape do not become interstellar visitors. Objects with sufficient velocity cannot be captured. The pattern is locked into the mechanics of motion, unchangeable, universal. Only took 3 examples to see the pattern clearly, but it will take thousands to map its full extent. The one pattern all interstellar visitors share is departure. It is written in their velocity, confirmed in their trajectories, unchangeable by any force the solar system possesses. They arrive as exiles and leave as exiles. Their paths through the solar system a brief intersection with a place they do not belong. The sun does not hold them. The planets do not capture them. They simply pass. Carrying the signature of systems that expelled them, moving toward no destination, bound for nowhere, traveling until they fade into the silence from which they briefly emerged. The pattern is absolute, and it is all they have in common. They left, and they will never return. The observations cease eventually. The telescopes turn to other targets. The automated surveys move on to scan different patches of sky. The last measurements are recorded and archived. The interstellar visitor, now too faint to detect, continues outward beyond the threshold of human instruments, its motion unchanged by the attention it briefly received. It crosses the orbit of Neptune. Then the heliopause the boundary where the solar wind yields to interstellar medium and enters the space between stars once more. The sun diminishes behind it, fading from a disk to a point, then to just another star among millions, indistinguishable from the background. The trajectory persists, carrying the object through the emptiness at speeds that seem fast by human measure, but are vanishingly slow across interstellar distances. Decades pass. Centuries. The visitor drifts through regions where matter is sparse, a few atoms per cubic centimeter, the thin gas and dust that fills the space between stellar systems. Occasionally, it passes through denser clouds, molecular regions where new stars are forming. But these encounters are brief and leave no mark. The object is too small, too cold, too inert to interact meaningfully with its surroundings. Millennia accumulate. The visitor travels light years from the sun, its trajectory a straight line through the galactic disk, perturbed only slightly by the gravitational pull of distant stars. The surface continues to darken under cosmic ray bombardment, the slow, steady rain of high-energy particles that never stops. Organic molecules on the surface break apart and recombine, forming complex polymers that deepen the reddish hue. Volatiles trapped beneath the surface sublimate occasionally when a cosmic ray deposits enough energy, releasing tiny puffs of gas that exert minute forces, altering the rotation imperceptibly. The visitor has no knowledge of its journey. It does not remember the system that formed it, the planet that scattered it, the star it once orbited. It carries no purpose, no destination, no intent. It simply moves, following the path determined by its velocity and the gravitational field through which it travels. Time means nothing to it. Distance means nothing. It exists in motion, a fragment of ancient processes, slowly eroding under forces too weak to notice, but relentless over geological time. Millions of years pass. The object may encounter another stellar system, passing through its outer regions, perhaps coming close enough for that system's telescopes, if any exist, to detect it briefly. Or it may miss all nearby stars, continuing through the emptiness for tens or hundreds of millions of years more, drifting through the spiral arm and into the space between arms, moving until chance brings it near another sun. The probabilities are low, but non-zero. The galaxy is large, and time is long. Eventually, the object will fade entirely. Collisions with interstellar gas, though rare, slowly ablate the surface. Radiation pressure from starlight, weak but persistent, exerts a drag. The object loses mass, atom by atom, molecule by molecule. Over billions of years, it erodes, diminishing from kilometers to meters to dust grains too small to hold together against the forces acting on them. The fragment disperses, its atoms mixing with the interstellar medium, becoming part of the raw material from which future stars and planets will form. The pattern completes, though not in any closed loop. The atoms that once comprised the visitor will drift in molecular clouds, condense in new protoplanetary disks, accrete into new planetesimals. Some will be incorporated into planets, buried in mantles or locked in minerals. Others will be ejected again, scattered by new planets forming in new systems, sent into interstellar space to wander anew. The cycle is not circular, but diffusive, matter spreading through the galaxy, mixing slowly, redistributing across light years and eons. The silence is complete. No record remains of the visitor's passage except the archived data from its brief detection positions, magnitudes, spectra stored in databases that will themselves erode eventually in their own way, as human civilizations change or fade. The object moves unseen, untracked, forgotten except as a catalog entry, a point in a statistical distribution, a confirmation of a pattern already known. In the outer solar system, another visitor may already be approaching, carrying the same hyperbolic signature, moving toward the moment when reflected sunlight will make it visible. Or perhaps it has already passed, undetected, its trajectory never intersecting a telescope's field of view. The galaxy is full of these travelers, and they pass continuously, most in silence, a few briefly illuminated by the light of stars they do not orbit. The stillness deepens. The stars wheel slowly in their orbits around the galactic center. The interstellar visitors drift among them, fragments of worlds scattered and wandering, bound for nowhere, returning to nothing, simply moving through the dark. The pattern persists, universal and unchanging, written into the motion of everything that was once bound and is now free. They left, and they continue leaving, indefinitely, into the silence that holds all things. Rest now. The visitors move on. The galaxy turns. The stillness remains,